This is the video lecture for section 4.2, which I'm calling expected value. The book actually has a longer title, but we're going to focus on expected value. And expected value is an application of the probability ideas that we were talking about in the last section. This is a real-world use of those probabilities. Let's start with the definition. The expected value of a random variable is an average value of the variable over the long run. So an expected value is essentially the mean value of the variable. And what it does is it weights that mean based on the likelihood of each of the outcomes of that random variable. The more likely a value of the variable is, the more weight it's given in the calculation of that mean. As the name implies, we can think of this expected value as a value of the variable that you can expect to see. But you have to remember that it's an average, so it might not be a possible value of the variable. We'll get into those ideas as we go. We have a formula for expected value. It looks a little technical, but we know what all these symbols mean. We just have to put it all together. It says expected value is given by, and then we have this funky sigma notation. Remember, that's the notation for a sum. So this is the sum of, we have brackets around these, so we're going to add up all things of this type. And what does this say? It says take each value of the variable and multiply it by its corresponding probability. So in other words, we're going to find all of the possible values of the variable. We're going to multiply each of those by their corresponding probability, and then we're going to add up all of those products. So it's the sum of the products of the values of the variable and their corresponding probabilities. I'm guessing this sounds complicated because we're talking about it abstractly, but if we were doing a specific example and we had a probability distribution table in front of us, you'll see that this formula isn't so bad. So let's begin with a couple examples from the previous lecture because we've already created the probability distribution tables for those and we can focus on the formula. Then we'll end with a few examples where we have to do everything, come up with the tables and follow the expected value formula. Let's begin with one of our favorite experiments, flipping coins. In section 4.1 we made a probability distribution table for the random variable number of tails in the experiment where we flip a coin 2 times. And you can see that table down below. We said that the probability of getting 0 tails was 1/4, the probability of getting 1 tail was 2/4 or 1/2, and the probability of getting 2 tails was 1/4. We're now going to take this example a step further and find the expected number of tails when you flip a coin 2 times. Now you may have some intuition for this. If you flip a coin 2 times, you might have a guess at how many tails you'll get on the average in the long run. But let's follow the formula and see what it says. Our formula is that the expected value is given by the sum of the products of each value of the variable and their corresponding probability. This is the sum of the products of each value of the variable and their corresponding probability. So I'm just going to follow that formula. First we do the products and then we add those products together. So I'm going to take each value of the variable and multiply it by its corresponding probability. 0 times 1/4, 1 times 2/4, and 2 times 1/4. What we're doing here is we're giving a weight to each value of the variable. And the more likely an outcome is, the more weight it's given because it has a larger probability. The outcome 1 is given a weight of 2/4 because it happens 2/4 or 1/2 of the time. The other two outcomes are given a weight of 1/4 because they only happen 1/4 of the time. So this is a way of giving more weight, more importance to a value of the variable based on its likelihood. Then we add all of those products together. 0 times 1/4 is 0. 1 times 2/4 is 2/4 because anything times 1 is itself. When we take 2 times 1/4, we're only going to take the 2 times the numerator of that fraction. We're multiplying by 2/1, not 2/2. This is also 2/4. Because I chose not to reduce, I'm guaranteed to have a common denominator, so I can add all these together. 0 plus 2/4 plus 2/4 is 4/4. And that gives us an answer of 1. That corresponds to an expected value of 1 tail. That expected value that we get is not a probability, it's counting a number of tails. It's counting a value of the variable. So we expect to get 1 tail. And if you think about it, that makes sense. If you flip a coin that's fair, you expect 50% of the flips to come up heads and 50% of the flips to come up tails. We know that doesn't have to happen in the short run, but in the long run, that's the expectation. So the expectation is that you'll average one tail per trial of this experiment over the long run. Short run could be different. You might get 2 heads 3 times in a row. That's not very likely, but it is possible. But over the long run, the expectation is that we'll average 1 tail per trial. And that's what this answer means. Now that's not a particularly engaging example because who cares about how many tails you get when you flip a coin 2 times, right? That doesn't matter. So the rest of my examples are going to deal with money, which most of us at least have some interest in. We're going to look at some simplistic examples from real life, and we're going to go back to the insurance example from the previous lesson. So we had this scenario where a person buys a 1-year life insurance policy for $250 with a payout to their family of $100,000 in the unfortunate event of their death. The insurance company is assuming that there's a 99.6% chance the person will survive. And since we did this from the perspective of the company, the random variable is the profit or loss for the company, we paired a profit of $250 with a probability of 0.996, because if the person survives, then the company keeps the $250. If there's a 99.6% chance of the person living, then there's a 0.4% chance that the person dies. The decimal version of that is 0.004. And if the person dies, the company pays out $100,000, but they took $250 up front, so we made the value of the random variable negative $99,750, and we paired that with the corresponding probability. What we're now going to do is take this an extra step and find the expected value of this policy from the perspective of the company. I don't want to jam this in at the bottom of this slide, so I'm going to put it on the next. We're going to find the expected value of the policy in the previous scenario, given this probability distribution. Again, we know that the expected value is given by multiplying each value of the variable by its corresponding probability, and then adding up those products. So we're going to multiply 250 by 0.996, and we're going to multiply negative 99,750 by 0.004, and you'll notice I've used parentheses to represent multiplication here. That's to avoid my decimal looking like it's attached to the 250. It also is going to separate this negative from the addition sign I'm going to throw in there. And where does that addition sign come from? This notation here tells us that we're finding the sum of these products. Now, unlike the arithmetic on the previous example, I'm not going to be able to do this mentally, so we're going to run to the calculator with this, and I'm actually going to do this in 2 different ways. I'm going to start by doing it the straightforward way, which is to just do all the calculations on the main screen, which isn't too bad here. But then I'm going to show you an alternative using a calculator function that we learned before. If I want to do this on the main screen, I can just type 250 times its probability, which was 0.996, plus, and then if you want to type a negative number, you want to use this little negation symbol down by the decimal point here. Don't use the subtraction symbol. The calculator will give you an error. So negative 99,750 multiplied by its probability, which was 0.004, and we get an expected value of negative 150. I'm going to show you that other way to use the calculator, but before we do that, let's interpret what this answer means. We're doing this from the perspective of the company, so if we get a negative answer like that, that's a loss of $150 per policy over the long run. In other words, if the company sells many policies of this type to similar people, they actually expect to lose money on these policies because their expected value is negative. If they only sell a couple of them, we can't really say what will happen. The expected value doesn't do a good job of telling us what will happen in the short term. But if the company is selling a lot of policies of this type, the expected value tells us that they should expect to lose money, which means one of 2 things. Either they need to adjust their rate and sell it at a higher cost to people of this type, or they need to lessen the payout of the policy in this scenario. If they don't do one of those 2 things, then they can expect to lose money in the long run. This doesn't guarantee that they'll lose money in the long run, but the more policies they sell, the more likely it is that their average will come down to this loss of $150 per policy. I want to make sure you understand that that's an average. So if they sell 1,000 policies like this, their expected loss is $150 per policy times 1,000 policies. That's a loss of $150,000. Think of this like we're the nerds down in the nerdery who have been hired to analyze the data. And we just crunch the numbers and we go back to our superiors and we're like, based on what we see, it looks like we're going to lose money on this policy. Okay, before we move on to another example, I want to show you another way that we can do this with the calculator. We can use our lists to do expected values. Let me clear this out. And I'm going to go to my lists. I'm going to press the stat key, choice number 1 to edit. And in list 1, I'm going to put the 2 possible values of the random variable. A gain of $250 or a loss of $99,750. And notice that I use the little negation key to type that negative number in there. If you don't, you'll get an error message. Now I'm going to use list 2. So I'm going to scroll over to the right, and next to each possible value of the random variable, I'm going to put in its corresponding probability. And I'm going to type these in as a decimal, but you could alternatively put them in as fractions. The calculator will then convert them to decimals. So the probability of a gain of $250 was 0.996, and the probability of this massive loss was 0.004. And now we've essentially recreated the table in our lists. I'm going to quit back to the main screen with second and the mode key. And there are a couple of different ways we could proceed from here, but I'm going to use that one-bar stats command. So I press stat, scroll to calc, and then remember, based on the type of calculator you have or the operating system that you're using, there are 2 different screens we could get. So I'm going to show you how to do it with both screens. When I push the 1 key in my current format, the one-bar stats prompt pops up on the main screen. And what I'm going to do is enter the 2 list names separated by a comma. So remember, to type a list name, you push second and the number of the list. So you always start with the list where the values of the variable were, which was L1. Then you type a comma. There's a comma button above your 7 key. And then you put in the name of the second list where the probabilities were. Mine are in L2. And we're going to get a bunch of outputs, but the one we care about is the mean, which the calculator calls X bar. And there's that negative 150 that we got by doing it on the main screen. For those of you with the stat wizard turned on, when you go to one-bar stats, you get this input screen. The first row, list, should be where your values of the variable were, and mine were in L1. Your second row, frequency list, should be where your probabilities were, and mine were in L2. Now that you've changed this to L2, it's going to stay like that until you alter it. So if you need to use just a single list in one-bar stats, you'll need to clear this out later. Scroll down to your calculate option and hit enter, and it will give you that same output screen. So hopefully these 2 examples have shown you that the formula really isn't that bad. It's not hard to use. But we did start with the crutch of doing examples that we had previously looked at, and the tables were already done. So let's do a brand new example from scratch, where we don't even have the probability distribution table yet. It says the blackjack player is given the option to double down on her $50 bet. Before I go any further, you don't need to know what it means to double down. I'll explain it in the example as we go. And when you get to the quiz or to the exam, you won't need any knowledge of games in order to do the problems. The information will be given. There's a 58% chance she will win, and if she wins, she'll profit $100 because she's doubling down on her $50 bet. She's basically betting an extra $50. There's a 34.6% chance she will lose, and since she's doubling her bet, that's a loss of $100. And there's a 7.4% chance of a push. A push is when the dealer and the player have the same total, and so that's like a tie, and so they don't exchange any money. The player gets to take back her $100. What is the expected value of her bet if she chooses to double down? Well, we know everything that can happen if she chooses to double down, and we know all of the probabilities. So we're going to first turn this into a table, and then we'll use the table to find the expected value. If you think you can find the expected value without making the table, you're welcome to do so. But every time a student struggles finding an expected value, the first thing I'm going to ask is, well, did you try making a table? Because that's the best way, in my opinion, to organize the information. So let's make a table of all of the possible outcomes and their corresponding probabilities. It says there's a 58% chance she will win, which is a profit of $100 because she doubled her bet. A profit of $100 would be a positive $100 from the player's perspective. And I'm going to represent that 58% chance by 0.58. You could alternatively use a fraction to represent that. You could use 58 over 100 or 29 over 50. I'm going to use the decimal because that's going to be the easiest way to translate it, in my opinion. It says there's a 34.6% chance she will lose, a loss of $100. If she loses $100, we want to represent that by negative 100. A common mistake is to put 0 here because the person didn't win any money. That's true, but they also weren't given back their bet. The casino takes your money when you lose. And so from the perspective of your bankroll, from the perspective of your overall worth, you now have $100 less than you used to. The probability that that happened was 34.6%, 0.346. And then there's a 7.4% chance of a push. That's the one we want to represent by 0. You break even when you push. The decimal here is 0.074. Now we have a table of everything that can happen in the experiment and the corresponding probabilities. Now we can use the expected value formula. We said that expected value is calculated by multiplying each value of the variable by its corresponding probability and then adding them all up. And in the previous two examples, I did that underneath the formula, as you can see here and here. But I want to show you a nice way that some students like to organize these problems a little bit further, and that's to extend this table to a third column. Rather than doing all of the writing underneath like I like to do, what a lot of my students have chosen to do, and it might be because the book does it like this, or maybe they came up with it on their own, but they'll just say, well, I know I want to multiply these numbers across, so I'll just make a third column and multiply across. So 100 times 0.58 is 58. And negative 100 times 0.346 is negative 34.6. And 0 times anything is 0. Then my students just add up this column. 58 plus negative 34.6 is 23.4. And we have our expected value. This says a positive number, so this is an expected gain of $23.40. And while there's nothing wrong with just writing 23.4, it's kind of standard in our money system to put that last decimal place. We go up to the hundredths place. So if the player chooses to double down, they expect to win in the long run. This is an expected gain of $23.40. Now, if you paid attention, you'll notice that you can't actually win $23.40 in this game. You have to remember that this is an average. This is an expected gain of $23.40 per play. An average of $23.40 each time. So if they made this bet 100 times, they'd expect to win $2,340. They wouldn't win exactly that amount, that's impossible, but they would expect to be close to that. That's what the expected value means. Let me demonstrate how to do this with the calculator again. I'm going to go to my lists by pressing Stat, choice number 1. I'm going to clear the old list. I'm going to scroll up to the list name, push clear, and the down arrow. We do that for L1. I'm going to use the arrows to get to the list name, clear, and the down arrow. In L1, we're going to put the possible values of the random variable. So 100, negative 100, make sure you use the little negation, and 0. Then the corresponding probabilities. The probability of winning $100 was 58%, 0.58. The probability of losing $100 was 34.6%, 0.346. And the probability of a push was 7.4%, 0.074. We're going to quit back to the main screen with second in the mode key. I'm only going to demonstrate it this time with the newer operating system because I've demonstrated both ways and that's how I have it set. So Stat, scroll to Calc, 1 bar stats command, L1 and L2 are what I want to use, so I don't need to make any changes here. I hit enter. And there's that $23.40 that we came up with when we did it on our own. The fact that the expected value came out positive probably wasn't shocking if you have a feel for what it means, because the player was going to win 58% of the time and lose only 34.6% of the time. Since the amount won and lost was equal, it's not shocking that the player would expect to win over the long run. But what I want to do is compare this to what would happen if she did not double down. And that's what I've got in the next scenario. Suppose the player in the previous example chooses not to double down. If you're not familiar with blackjack, and maybe you don't care, but I just feel like I should explain, if you double down, you only get one more card. You don't get to keep taking them. If you choose not to double down, then you can take more than one card, and so that's going to change the likelihood of winning and losing. If she chooses not to double down, it actually gives her a better chance to win. It gives her a 66% chance of winning instead of the 58% chance she had by doubling down. However, her profit is only $50 in that case because she's not doubling her bet. She only has a 25% chance to lose. Her probability of losing has decreased because of the extra cards that she can take. And it turns out that her chance to push increases slightly. She's got a 9% chance to push. What is her expected value in this case? And then should she double down or not? And we're going to base that decision on the expected value. Let's make a table of the possible outcomes. We know that there are three possible outcomes. She did not double her bet, so she could win $50, she could lose $50, or in the case of a push, she'll break even. We said that there was a 66% chance that she'll win, there's a 25% chance that she will lose, and there's a 9% chance that she'll break even. So the way I like to organize it is to actually do the arithmetic off to the side. I write the formula out. I'll multiply each outcome by its corresponding probability. I'm going to use those parentheses again just so that it looks nice. 50 times 0.66 is 33, and negative 50 times 0.25 is negative 12.5. 0 times anything is 0. I subtract here and I get 20.5. So that's an expected gain of $20.50. Now it dawns on me that this is kind of an old school way to do it, because I'm an old person. You might find it a bit more convenient to do it this way by extending the table. It's the same concept, you just don't write everything out, so it's a little more streamlined. You still take 50 times 0.66, but instead of writing it out like I do, you just write the result in the third column. You still take negative 50 times 0.25, you just write the result in this column instead of writing out the work. Same thing with all the other calculations you might do. And then you can just add down the column. Same result. And of course the third option is to use the calculator. And since I've demonstrated with the newer operating system twice, let me do this example with the older operating system. I go to my lists, clear them out. I'm going to enter the values of the variable in L1. Make sure you use the little negation key for negative 50. I enter the corresponding probabilities in L2. I quit back to the main screen with second in the mode key. Stat, scroll to calc. And if you're using the older operating system, or if your stat wizards are turned off with the newer operating system, you get the 1-bar stats prompt on your main screen. So I push second and the 1 key to type in the L1, that's where my variable is. Then you press the comma button, it's right above the 7 key. And then put in the name of the list where your probabilities are. For me, that's L2, so second and the 2 key. Hit enter, and there's that $20.50 that we came up with. Again, that's an expected gain per play of $20.50. Over the long run, you'd expect to win $20.50 on the average for each time that you've played the game. If she had chosen to double down, we said she'd come up with $23.40. That's a larger expected value. And so in the long run, it's to her advantage to double down. Note that you can't just base it on her probability of winning or losing. In the first scenario, she had a 58% chance of winning. In the second scenario, it increased to 66%. She's actually more likely to win money in the second scenario. But you can't just base things on the probability because there are different amounts of money involved. When she chooses to double down, it's doubling her profit when she wins. It's close, but it actually gives her a little bit more of an advantage against the house if she doubles down in that scenario. And so over the long run, that's what she'd want to do. Unless she's counting cards or something and has some extra information. But that's a discussion for another much more interesting class. One more real-world scenario. I admit I worded this one a little bit funny because I want to make sure you understand what the random variable is. We'll get to that at the end of the problem here. It says you park in a metered spot and choose not to feed the meter, saving you the $1 that you'd have to pay to park in that spot. If you get caught, though, you'll have to pay a $100 parking ticket. Let's assume the probability that you'll be caught is 2%. What is your expected value of the change in your net worth if you choose not to pay for parking? And while that might be a little bit verbose, it makes it clear that what we're doing is just asking what happens to your overall amount of money. It's a little bit technical, but I thought this wording would avoid any confusion along those lines. We're just going to look at the expected value of the change in your net worth if you don't pay for parking. We're going to start by making a table of the possible outcomes. Again, the variable here is the change in your net worth. If you don't pay for parking and you don't get caught, then you don't lose any money. Your net worth doesn't change at all. If you do get caught, then you have to pay a $100 parking ticket, and so your net worth is going to decrease by $100. I know that's a weird way to word it, but if you don't define the variable precisely, then the question would be, well, is X the amount of money that you've earned by not paying it? Like you have an extra $1, so should X be 1? So I just tried to make it clear by saying it's the change in your net worth. Either your net worth doesn't change at all because you got away with it and you didn't have to pay for parking, or you lost $100 because you got caught and now you have to pay a ticket. It says there's a 2% chance you'll get caught. Which outcome corresponds to getting caught? Well, the loss of $100. So we're going to pair the 0.02 with negative 100. And notice that it's 0.02, not 0.2. 0.2 is 20%. It doesn't give us the probability that we won't get caught. But remember, getting caught and not getting caught are complements. And so if there's a 2% chance you will get caught, there's a 98% chance that you won't get caught. And now we can calculate the expected value. I'm going to stick with my favorite way, which is to write it out. You can choose to try this by extending the table or by using the calculator. I take 0 times 0.98, and I add that to negative 100 times 0.02. 0 times anything is 0. Negative 100 times 0.02 is negative 2. And so we get an expected value of negative $2. That's an expected loss of $2. Now how can we make sense of this answer? Well, if you just paid for parking, your expected loss would be $1 because it was a $1 cost to park. So in the long run, with this scenario, with the assumption that you're going to have to pay the fine 2% of the time, it's actually cheaper for you in the long run to just pay for parking. This is in fact why parking tickets cost so much, because they don't catch very many people, but the people they do catch make up for the parking not paid by the people that they don't catch. They might not catch very many people, but the ones that they do catch make up for the ones that they don't. Now, maybe that 2% isn't realistic. Maybe they only catch 1% of people, or maybe they catch more than 2% of people. That was just a guess that we made. But under that assumption, it's actually going to be cheaper in the long run for people in general if they just paid the meter. An individual might get lucky and get away with it more often. But on the average, for all people who do this, they expect to lose money. Okay, this ends the section, which happens to be one of my favorites in the whole course. And this is something that I personally use a lot as a game player. I'm really into this stuff. But I know it can be complicated and there are a lot of things to wrap your head around. So please don't be afraid to contact me, shoot me an email, or catch me in an office hour if you have any questions.